All right, in this chapter, we're going to talk about nuclear chem. Nuclear chem is kind of different from other chapters in the sense that we're going to see a lot of stuff specifically about the nucleus that doesn't really apply to other chapters. So this is, in a way, a standalone chapter, but it does revisit a lot of the concepts that we've covered when we discovered the atom and the subatomic particles 2 chapters ago. So what we're after in this chapter is to understand how atoms form, in the sense of, why do those protons stick together in the center when there's so much repulsion? What is the purpose of the neutron and why they're in the nucleus with the protons? And then we're not really going to see much about electrons in this chapter because this is nuclear chemistry. It focuses mostly on the nucleus, so protons and neutrons and their interchangeability. We're also going to look at nuclear reactions, talk about half-life and how atoms fall apart, and how you can use that calculation to go back and see how old things have been sitting in the ice, say if it were a woolly mammoth or something of that nature. And then a little bit about the history of nuclear through wars and through power and so forth. So what I want to start by introducing nuclear reactions is just to understand that this is how you change atoms. There is no other way to change an atom that we know of. You can change protons to neutrons and neutrons to protons, and this is really the only way to make carbon into, say, nitrogen. Everything else that we really talk about in this semester is based on charge, and that's changing electrons, not the protons. So some major differences you can expect to see from this chapter and other chapters that we cover, because this is really, again, a standalone chapter, is that in chemical reactions, carbon's still carbon. It's just going to have a new charge if it's gaining or losing electrons. And that's the focus for most of our semester. In a nuclear reaction, you're changing the element completely by changing its protons. So it's going to be a completely different element with completely different chemistry afterwards. When we deal with chemical reactions, we're typically dealing with valence electrons. So these are the electrons on the outermost edge. We just scratched the surface of what that means in our last chapter with electron configuration. And then again, because this is nuclear reaction, it sounds scary, but it's really just the nucleus. It's the center of the atom, and now it's changing. It has nothing to do with electrons, although electrons can be produced or absorbed, captured in a sense, into the nucleus, and that can help change it. And we'll talk about those individually coming up. One thing unique about a chemical reaction is temperature can speed up a chemical reaction very fast. So you can imagine if your cell phone is sitting on a hot dash in the summer, its battery can go dead really quickly. Or if a cell phone is sitting in your car when it's in the winter and it's very cold, it discharges very slowly. So temperature and chemical reactions go hand in hand. As temperature goes up, the kinetics of that reaction typically go up with it, and vice versa. In a nuclear reaction, you can be hundreds of millions of degrees in the sun, and the reaction is going to happen at the same rate, so it's independent of temperature altogether. The energy of most chemical reactions, can take down, can burn wood, can, make a car move. There's pretty large explosions given the right kind of circumstances and, dynamite, things like that. But most of them are pretty small scale. So you're thinking about, blowing up a building at most with a chemical reaction, whereas a nuclear reaction, you can take down a whole city, maybe a whole county in the case of the thermonuclear weapons. And that really just depends on, are you changing the outside of the atom or are you changing the inside? And that makes a huge difference. Also, what we talked about several chapters ago was law of conservation of mass, and mass is conserved. So if you start with 10 grams in a chemical reaction, you're going to end up with 10 grams after the chemical reaction's over. So the reactants always equal the products in the amount of mass. However, in a nuclear reaction, you can convert some of that mass to energy or vice versa, and that's through Einstein's equation, E equals mc squared. So there's substantial differences between normal chemistry and in what we call this chapter, nuclear chemistry. So nuclear chemistry really began with alchemy, this idea that you can make magical potions, you can make new elements using magical rocks to make magical potions. A lot of these are made famous in the things like the Harry Potter series with the Philosopher's Stone and so forth. Much like all alchemy, whether it's in video games or books or both, is, it's magic based. There's no chemistry behind it. There is no magical potion that I know of or that anybody knows of that can change elements one to another, turn people into monsters or whatever. That's all in the movies. But what is important is this is where science fiction and science kind of began, because they tried making these magical potions. They just never succeeded. So let's talk about two famous alchemists real quick, just to give you kind of an example of what kinds of nuclear chemistry was thought about but never really accomplished. So in about 8th century Egypt, we have a alchemist named, at least nicknamed Geber. His Arabic name's there as well. He was really into transmutation, so this ability to change elements, which is capable in the modern time. Now we can make elements, transmute them from smaller elements, but it takes nuclear chemistry. And what Geber was doing potentially in his tent out in the desert was normal chemistry. So he was changing electrons, and that was never going to change elements from one into another. It didn't keep him from trying, but he was never going to be successful in that kind of scale. Not only did he want to turn things into gold, because gold was very valuable back then, all those Egyptian pharaohs and so forth, they wanted lots of gold, and if they could take simpler and cheaper elements and turn them into gold, they would pay lots of money for scientists or alchemists in those days to try it. Another one of his hobbies was to artificially create life. So he wanted to make new humans, new scorpions, new snakes, all out of chemical potions and magic. And again, that never really happened either. So this was really the birth of scientific research, in the sense of just trying things and see what happens. Did that lead to explosions or, loss of eyebrows? Probably. But this idea of changing new elements really started with Geber. He was probably the most famous for it, even though he was never successful. About 8 centuries later, another famous alchemist named Paracelsus was more into the medicinal field. So for those in the allied health kind of group, this is a person that kind of led your field in the sense of understanding the human body, understanding, toxicology, understanding surgery. He even introduced what we call the germ theory. So these microscopic organisms that cause our sicknesses is really his idea that started that whole conversation and that area of research. Most of the things that he did was based on his own medicine. So he made medicine based on things that he could find in the woods, things that he could find along creeks and roots and berries and so forth. The easiest way to practice was to test it on himself. If the medicine made him feel better, he would make a note of it and then prescribe it to some of his patients. If the medicine that he made him very sick, and assuming he didn't die, because then the medicine research would stop, but if things made him sick, he would know to stay away from those kinds of combinations. He was another alchemist that claimed to find this magical rock called the Philosopher's Stone. With this magical rock, he could make a magical potion to live forever. So it's that, immortality that he sought more so than with Geber, who was really just trying to turn things into gold or to make humans from scratch. So by having this magical stone and making this magical potion, he created this elixir of life, he said. And eventually he died at the age of 50. But if you think about it, back in those days, most people didn't live past their 30s. So for a long time, people probably believed that he made that magical, immortality elixir. So as we start to better understand nuclear chemistry, we have to realize there's an important feature that kind of disproves, in a sense, that mass is conserved. It is conserved in chemical reactions, but in nuclear reactions, that's not the case. So what you see in this slide here is something unique, and that's that if you were to weigh the pieces, so these guys over here, these pieces are the exact same pieces in a carbon-12 atom. So what they're saying here with the mass defect is the sum of the pieces is actually more than the atom itself, which in mathematics that would be impossible. But he introduced chemistry with mathematics, and things get a little bit more complicated, because now we can see that through Einstein's equation of E equals mc squared, something unique about that is energy and mass can interconvert. And we need energy to hold the nucleus together. So c is the speed of light, 3.00 times 10 to the 8th meters per second. That's really irrelevant for our class. It's just a big number, and when you square it, it gets bigger. But this tells you that a small amount of mass times a huge number gives you a decent amount of energy, and that's what we're seeing here. So even though our mass is missing over here, because we are, lighter on the right than we are on the left, even though we're basically the same amount of particles, it tells us that in order for these pieces to come together into an atom, we're going to have to change some of that mass into energy. And that energy is exactly what holds the nucleus together. It holds those subatomic particles together. So the reality is protons don't want to be next to protons. But with the help of neutrons, it's a little bit easier for them to deal with each other in that relatively confined, small marble-like space, in the sense of our stadium analogy. But just know that some of that mass is missing, and it's converted to energy to hold that nucleus together. Eventually, though, that is not the case, because nuclei will fall apart and become radioactive if it's too big and too positive. So what we see with binding energy, which is really the E of the E equals mc squared idea, where binding energy and mass defect kind of are interrelated in that sense. You could think of mass defect as the M and binding energy as the E. But here we can see that up here at the top with iron, we have one of our most stable nuclei. So if we have one of our most stable nuclei up here, that's important for our planet, because notice our core of our planet is mostly iron. So for it to be super stable, in the sense it has the most amount of energy holding its nucleus together, it's very unlikely to be, unstable, radioactive, and fall apart. And we don't want the center of our atom, center of our planet falling apart. What we also see as we go down versus when we go up, as we go down, we have less energy. And that tells us that the repulsion of those atoms eventually gets to a point where there is no amount of energy that's going to hold it together, and they're just going to fall apart. And that's what radioactive atoms tend to do. It's just too much positive to survive. We also see that as we approach more and more energy, our smaller atoms, the ones down here, they don't need a whole lot of energy, and that's because they don't have a whole lot of positive to hold together. So the reality is iron has the most energy holding it together. Other atoms are close, but eventually as you get too big, there's no amount of energy that can hold your nucleus together. And when you're small, you just don't need a lot of energy to hold your nucleus together, and that's the reality of it. One problem Geber had in his, goal of making gold from other, similar but different elements, is that he was doing chemical reactions. His reactions were probably in the, 1,000 kilojoule kind of range. So what we're doing here is comparing a chemical reaction, which is maybe 1,000 kilojoules. So these are, a chemical reaction in size and in scope, and that, this would be a pretty good one. But in order to do a nuclear reaction, he needed to be doing billions. So billions would be, many more zeros. So here's a million, add more zeros, you get 1 billion kilojoules for a nuclear reaction, because again, nuclear and nucleus are the same thing. And that's why it never happened. The ability to generate that amount of energy in a tent out in the desert in the 8th century was never going to happen. And now our 21st century, we can make elements. At the end of the 1990s and so forth, they started making some of those, and we finally completed our 118 elements of the periodic table by doing so. But he was kind of like the big bad wolf. He was pushing on those protons and neutrons, and it never happened. He could never change them meaningfully, because he was doing chemical reactions on the valence electrons. He was not touching the nucleus in any shape or form to change those atoms. So as we mentioned, radioactivity is just this ability for the nucleus to be unstable. So what we can see from this chart is the larger we get, the more neutrons we're going to need. So notice this red line here is a neutron to proton ratio of 1:1. So that means you're half and half. So if we go down here, if you're 20 protons and you're 20 neutrons, you're going to be right on the line. And that's kind of the magic number for where it is 1:1. And we can kind of see that on the periodic table, because calcium's got 20 protons, but it's got an average mass of 40. But after that, notice this chart starts leaning heavy towards that neutron side. And that tells us that the more positive we get, the more cushion we're going to need, or we're going to fall apart, because up here, notice, there is no amount of neutron-proton combinations that are going to be stable, with the exception of this small little island of stability. All of this space over here and over here just shows you that there's a lot of combinations that are radioactive, that aren't going to be stable. So what we're going to teach you in a separate video coming up is, if you want to be stable, and you are an atom that's over here, there's ways to move left, and if you're over here, there's ways to move right. So you can change protons to neutrons or neutrons to protons in order to become more stable. Sometimes it takes multiple steps for that to happen. But the take-home message for here is, notice that after the magic number 20, so in this kind of situation here, after 20, we start to get heavy on the neutrons, and that's very important for what we see in the periodic table. And now we know why. Too much positive is unstable, and there's no amount of neutrons that can make it stable eventually. So remember, neutrons do have a very important role. They're kind of like the referee. They're like the pillow between protons, but eventually there's no amount of pillows that can hold so many protons apart, and that repulsion overtakes the atom, and then they fall into smaller atoms, and that's what radioactive really is. So as we look at this magic number 20, again, notice that we're really creeping heavy on the neutron side. If we were to zoom in a little bit on this next slide, you can kind of see the isotopes of carbon that we mentioned in a previous video. When we talked about isotopes, carbon-12 is the most stable. It's got 6 and 6. We can see that it's the most stable because of its average mass of 12.01 on the periodic table. So most carbon is carbon-12, and it is half and half protons, half neutrons, with 6 each. As we approach 7 neutrons, we're getting above the band of stability. You'll see a matching section in the homework over this. But as we get too far, what happens with carbon-14, we'd have to go way down here in order to see it. But imagine this little tick mark here is about 10. So carbon, as we get to carbon-14, we're going to go over 6 and then up 8. And you're going to be right off the edge of that brown band of stability. And that's what tells us that something with too many neutrons, in the case of carbon-14, that's when we become radioactive. We're getting off that brown band of stability into this kind of ocean of radioactivity out here, where atoms can't exist, where there's no proton-neutron combinations that are known to be stable exist. So everything in that kind of white grid pattern is radioactive. And really what atoms want before they can become noble gases is to kind of swim to that band of stability. And again, we have multiple ways of doing that. We can move left on the periodic table, or we can move right. And those are processes that we're going to show you coming up. So as we start to think about how atoms fall apart, it's really just a math process. It's called half-life. So when a nucleus is unstable, it reduces its mass by half of its initial amount over a certain amount of time. That's called half-life. So very specifically, it reduces its mass by half. So you're really just dividing by 2 as many times as it takes to get to the total time given. So imagine here, if you have a 30 microgram dose of this iodine 123, what you'll notice about it is you have a half-life of 13.1 hours. So you want to know how much time is, how much mass is left after 39.1 hours. That's just 3 times the half-life. So that really just means you're going to reduce the mass of 30 3 times. So you're going to cut it in half 3 times. So you'll take 30 and then you'll divide it by 2. So in one half-life, or 13 hours, you're going to have 15 micrograms left. If you divide it by 2, you're going to get 7.5. And that's going to be after 2 half-lives. And then after, so about 26.2 hours. And then when you divide by 2 again, you're going to get the answer of 3.5 micrograms. And that's going to tell you how much mass to expect to see after that allotted time. So notice we have 1 half-life, 2 half-lives, 3 half-lives. That totals are 39.3 hours. So it's really just a divide by 2 kind of process. So as we switch gears to our nuclear change kind of video, we're going to talk about particles first, and then we're going to talk about the reactions using those particles second. So we'll catch you then.